Hello, in this session we are going to look at vectors and transformations. In an earlier session I've talked about vectors and talked about some of the ways that you use them. Right, and I've talked about how a vector, how you might think of it as an arrow pointing in a certain direction, and that it is basically a quantity that tells you the length and that tells you the magnitude, that means the size, and the direction, and it can be used to describe anything that has a magnitude and direction, like a force or a displacement or velocity and so on. And that you can describe a vector by two numbers, one number being the magnitude, like for example you can say that the magnitude of this is 5, and 5 can be the force, like 5 newtons, or distance like 5 meters and so on, and a direction. And the direction, you might describe that you would need a reference direction, for example to the north, and this might be a certain angle like 20 degrees, so you can say that the direction is so many degrees to the north. So that's a vector. Now in this session we are going to look at another way of describing this same information, to describe this same information about the direction and the angle. And the way to do that is to think of a graph with a x and a y-axis. Okay, if you're on a graph, you can imagine drawing an arrow or a vector with the tail end at the origin, and the tip of the arrow would be somewhere on the graph. If you draw that, then there is another way that you can describe a vector. You can make use of the position of that arrow, the position of the tip of that arrow on the graph. So let's say, for example, the x value is 4 and the y value of the point is 3. So in a sense, the 4 and the 3 is an equally good description, equally good as the magnitude and the distance. That means that if instead of telling you the magnitude and the angle, I tell you the x and the y value on the graph paper, then you can actually draw the same vector simply by going to that point and drawing a line pointing from 0 to that point. So the information using x and y is an equally good way to represent or to describe the vector. It contains the same information. You can convert between x, y and length and angle. Alright? So that's another way to describe a vector. And in the last session I talked about matrix. Now we can simply write this information 4 and 3 and arrange them in the form of a matrix. So one way to do that is to write 4, 3. So that's like a matrix with 2 columns and 1 row. Right? Another way that is also often used is by writing 4 and a 3 below that. Okay, and that's a matrix with 2 rows and 1 column. Now, we often call this a column matrix, and in this session we will we will mostly be looking at this way of writing the two numbers, because the idea is that we can then make use of what we've learned in matrices, the kind of calculations that we've learned, to do different things with this vector and this point here. So one thing that we could do is to see how we would add vectors. Using this way to represent a vector with the x and y values, there is actually a very easy way to add two vectors. Now let's refresh our memory on how to add vectors. Suppose I have two vectors, right, A and B. Okay, put a little, if you remember, I like to put a little squiggle below it to show that it's not just a number, but it's actually a vector. If I have two vectors, the way to add there are two ways to add the vectors. One is called the triangle law of addition. One is called the parallelogram law. So I've talked about both of these in the earlier session on vectors. I'm going to make use of the well, I'll just talk about both. Right, if we think about the parallelogram law, I would just imagine that these two lines are the sides of a parallelogram, and I would complete the parallelogram like that. By drawing the other two sides, alright, the parallel sides. And then this point up there would be the resultant, the result of adding the two vectors. So that's how we do it. And in the triangle law, instead of drawing out the full parallelogram, I would imagine taking this vector and shifting it until its tail touches the tip of the other vector, so that, meaning that you just draw one side of the one more side of the parallelogram, and then you complete this triangle, okay, by drawing an additional line here, and it's really the same line and it gives you the same resultants. Okay, so this is how you add vectors. Essentially by drawing. Now using this column matrix, using this way of writing a vector with the two numbers that are the x and y values, we have another way which is even simpler. Now to see how that works, let me draw the axis, the x and y axis. Right, so suppose that I represent each of these vectors by the x and y values. So let's say this point here is 3, 1, and that point up there is 1, 2. Right, so I have now the two sets of x and y values that represent the two vectors. Now if I look at the vector A, think about what the 3 and the 1 means. It's the x and y values. That means that the x value means this point here is 3. If you drop a perpendicular from the tip of the vector to the x-axis, and if you go horizontally from the tip to the y-axis, it's a 1. Okay. Now you can think about this getting from the origin to the tip of the arrow by moving 3 units from the origin, 3 units to the right, and then 1 unit up. So 1, 2, 3 to the right and 1 unit up, and you will reach the tip of A. Now likewise, for the other arrow, the tip is at the y value of 2 and x value of 1. And you can imagine going from the origin to the tip of that arrow by moving 1 unit to the right and 2 units up. Right. So how can I then get to that point, which is the answer that we want? Well, because this line is really the same as that line, same meaning, same length and same direction, they're parallel. Now I can imagine starting from that point and going to that point by moving 1 unit to the right and 2 units up. Alright, because that's how I got from the origin to the tip of B. Alright, 1 unit to the right, 2 units up. So from the tip of A, if I move 1 unit to the right and 2 units up, I get to that point. So 1 unit to the right and 2 units up. So what this really means is that in order to get here, I have to start from this point, which has the x and y value of 3 and 1. So I must add 1 to the 3, to the x value, and I must add 2 to the y value in order to get here. So 3, alright, starting from 3, I move 1 unit to the right. So 3 becomes 4, and I move 2 units out, so 1 becomes 2. Alright, and this gives us a very simple way to actually find the answer. You just see that what I've simply done is to add the x values of the two vectors to get 4 and the y values of the two vectors to get 2. Now let me write both of these in column matrix form. 3, 1, so my vector, if I want to find A plus B to get my answer, which I'll call it C, the resultant vector, I can do it by writing A in this column vector or column matrix or column vector form, which is 3, 1, and B, which is 1, 2, and I can simply add the x values, 3 plus 1, get 4, and the y value 1 plus 2 to get 3, and that would be my resultant. You can see that it's now quite simple. All I need to do is two simple additions, and you don't even have to draw the parallelogram. Of course, you can only do it if you already have the x and the y values. What if you don't? You have to find it. You can find it by, for example, actually drawing it out on a piece of graph paper. So that means you still need to draw something. Or you can find it using trigonometry. Alright, because this is a triangle. For example, if you know the length, 5, and the angle of some value, then because this is a triangle, you can then use trigonometry, sines and cosines, to find this side and that side. I shan't go into that at the moment, but that's addition using matrices. Next, we're going to look at transformations. Let's start on the graph paper and think about a point on the graph paper with a x value of 1 and a y value of 2. Now, transformation is about moving points and shapes of figures around on the graph paper. Basically, that's the main thing, the main kind of transformation we'll look at O level. Now, and the ways that we can move this point around is, there are a few ways that we'll look at. The first and simplest is called translation. That means that if I take this point and move it to another point, and if I always do the same movement for any point that I have on the graph, that's called a translation. Now, again, if you are thinking of seeing this for the first time, it may seem rather strange why you want to do this. There are certain uses, especially when people have to do calculations in geometry and in designs and physics and engineering and as well as many other areas of science and economics. But what we are mainly going to look at is, if you like, a set of rules, all right, to tell us how we can do certain things on the graph paper and move the points and figures around in a certain way. So just treat it as a set of rules and like a little game, if you like, even though you might or might not like it. It's basically a set of rules that we're going to learn, and in this rule, which is called a translation, we learn one way that we can move points around on this xy plane. So, for example, the translation is basically a rule that tells us that we'll move any points by a certain distance in a certain direction. So, for example, if I take this point, and the translation is that I can move it by this distance, okay, say this is right 2 units to the right and 1 unit up, and if I have any other point, for example there, got at A, got at B, I would do the same, and so on. That's a translation. Okay, and to describe such a translation, we use what is called a translation vector, given by this 2 and 1, which we can write in the matrix form. Now, the idea is that if you are given any points on the graph, for example, if you're given B, that B has coordinates of say -3, -4. Okay, so point B has these x and y values. Now we say that we can apply a translation to B, and when we apply this translation, the point B moves from this point to that point, and we can find the new points let's say I call it B primed. There's B with a stroke next to it. I can find this point B prime simply by adding the translation vector. So B, which is this vector, goes to, or is transformed to, or we can even say it is mapped to, if you have learned, if you have seen the previous session on functions. Right, B is mapped to, let me write it this way, that's B, is mapped to B primed, which is given by B itself plus the translation vector. Okay, all we need is to add the two vectors, and we get minus 4 plus 2 is minus 2, minus 3 plus 1 is minus 2. There we have our new point, the point B that we get after applying this translation to B. And in the same way, if you have any other point, like A or maybe C, as long as you know the x and y values, you can just add the translation vector to get a new point. So this is translation. We're still on translation. Now, moving a point is quite simple and maybe a little bit boring. Now what we could also do is to move a figure. Suppose that I have a triangle and I want to do a translation to it. Okay, with a translation vector of, again, 2, 1. So how would I apply a translation to a whole figure? The way is to find out the coordinate, the x and y values of each point. So let's say this point A is 1 and 1, point B is 3 and say 1.5, point C is 2 and 3. Alright? In order to find the new points, the new position of this triangle, we would add to these x and y values the translation vector itself. So for A, to find the new point, we would take 1, 1, and this will go to 1, 1 plus 2, 1. And when we add them, we'll get 3 and 2. And for point B, in the same way, we would take 3, 1, the x and y values, and add 2, 1. So this will go to 3, 1 plus 2, 1, which is 5, 2. And we will just repeat this for B, not for C. So once we have, so for each of these steps, we will get the x and y values for the new positions of A, B, and C. and then we can put them on the graph. So the new positions might be, for example, A might go to there, maybe there, B might go to there, C might go to there, and then we simply draw the new figure there. So we have a new figure and a translation. We're going to look at reflection next. Now suppose I have a point there with x and y of 1 and 2. Now imagine that the x-axis is a mirror. So we are looking at reflection in the x-axis. If the x-axis is a mirror, and I call this point A, then A will have an image down here, which I call A prime. And we know that the image must be at the same distance behind the mirror. So this is minus 2 would be the y value of the image. Okay, and you can imagine that if you have a whole figure, like a triangle just now, we can simply do a reflection of the whole triangle by doing a reflection for each point on the triangle. So, just as an example, let me draw a triangle here, A, B, C. And B will be reflected there, C reflected there, and I have a reflection of the triangle down here. As with translation, we want to learn about how to find the coordinates, the x and y values of the point after the reflection. So for example, we have seen how to do it for A. It's quite simple. You simply take the y value and change it to a negative number, and the one stays the same. So it's fairly straightforward. Now what we are going to do is to make use of matrices to help us to calculate the new position. Now it might seem a bit unnecessary, because if it's so simple just to change the y value, why bother to use matrices? The reason is because later on we are going to look at slightly more complicated transformation where it is not so easy to find the new positions of the point. So what we could do is to make use of this very simple example to see how we can actually apply matrices to find the new position. Now I'm just going to write out the method first, and then I will explain. If I have a point A and the x and y values are given by 1 and 2. Okay, I want to find the position of A prime, the position after A is reflected in the x-axis. And the way to do it using matrices is to multiply this 1, 2, this column vector, by a matrix. And that matrix is 1, minus 1, 1, 0. Now when you multiply this matrix, you take, to get the first number, you multiply the first row by the first column. You multiply the number by the corresponding number. So 1 times 1, which is 1, minus 1 times 2, which is minus 2. And you do that for the second number, second row and first column. So 0 times 1, which is 0, 1 times 2, which is 2. And the answer is right, it looks like I've done something wrong here. I've got the wrong matrix. Let me start over. Sorry about that. The correct matrix should be 1, 0, minus 1. That's the correct matrix. Now let me multiply that out again. To get the first number, look at the first row and the first column. So 1 times 1 gives you 1. 0 times 2 is 0. To get the next number, you take the second row and the first column. 0 times 1 is 0. Minus 1 times 2 is minus 2. So you get 1 minus 2, 1 minus 2, which is the correct position, A primed. And the idea is that you can apply that to any point. If you have this point B, for example, let's say that's 3 and 2.5. So B is 3 and 2.5. I can find a new position B prime if I multiply the vector B by the same matrix, 1, 0, minus 1, 0. And you'll find that the answer, when you carry out the multiplication, is 3 and minus 2.5. And that gives the position of B. So that's the idea of using a matrix. Now, why does it work? The reason why it works is that we know, in this example, that we really just need to change the y value to negative, or just to change the sign of the y value. So if it's negative, you change it to positive, for example. And this matrix does that. Now you can see that when I do the multiplication, I multiply these are the x and y values. I multiply the x value by the 1 here. The y value is just multiplied by 0 when I try to get the first value. So when I get the new value of x, it always ends up giving the same value as the original x value because it's just multiplied by the 1. Alright, to get the new x value. And for the y value, I get it by multiplying the first row by the first column. But the first number in the vector is always multiplied by 0. Okay, so I can ignore that. And the y value is always multiplied by a minus 1, which is why the sign is changed. So that's the effect that the matrix has on the x and y values. This particular matrix, the effect of this particular matrix when you multiply is only to change the sign of the y value. So that's why if you apply it to any other column vectors, you get the same effect. The y value has the sign changed. The x remained the same. We'll stop here for this session. See you next time.